Okay.
Yes.
Yours.
Yeah. Yes.
Now, as already it was said by Professor Aresta in this morning, in the morning session, the CO2 molecule, it's not anymore a simple waste product, but this is a central carbon feedstock for the renewable chemical economy. And through photoelectrochemical CO2 reduction, we can transform CO2 molecule into fuels, chemicals, synthetic rubber precursors, bioplastics, or a broad spectrum of industrial feedstock. So this positions CO2 as a central building block for a future carbon economy. But it's not a simple story to break the symmetry of the CO2 reduction, and this is the condition for the transformation of CO2 towards valuable products, and especially this is a precondition to get the C2 plus products. The breaking linear condition, it's determined by the good absorption and production of the CO radicals. And from a theoretical point of view and from experimental point of view, the absorption of the CO2 is determined by the properties of the surface, and this is our motivation. So the motivation of our work is to keep the electronic structure of the semiconductor itself and affect the absorption energy, the absorption symmetry, to break the linear structure of the CO2. So once we are at the surface, that's clear that we are working with the substrate, but the driving force for this process, which occurs at the surface, it's going in the bulk, in the structure. So the absorption of the light, production of the charge carriers within specific time scales, these are very sensitive steps in the CO2 reduction, and what else? All these elements must occur at the same time. So this is challenging. So the challenge lies down in the material structure, in the material's surface, and the progress might be done to take into account all together. So it becomes clear that we need a hybrid system where the weaknesses of the material compensate by the improvement of the surface or by the complementary second phase. Here you can see the copper oxide morphology, since we choose this material as a background material, as a base material. And the reason for that is that copper 1 oxide, this is the material which is able to carry out the reduction of CO2 towards C2 products. So you see the morphology, it's very good for the photoelectrochemical reduction of the CO2 and allows impregnation and entrance of CO2 intermediates within the semiconductor structure. However,
Sorry.
Yes.
If you are changing the slides, we still see slide number 3 and also online.
Okay. Now
is 4. Now is 4.
Yeah, I was talking about the theoretical and the absorption, the geometry, and here we are at the time scale. So we need the properties, which are properties of the bulk together, absorption, charge transfer, and the catalytic activity all together. And this is the condition of good performance. And here we are at the morphology of the copper 1 oxide, and you see on the left side the morphology of the copper 1 oxide itself. And what happens on the left side, this is this morphology of the copper 1 oxide after photoelectrochemical run. And depending on the cutting of filter, we can produce different morphology of the copper and metallic copper nanoparticles. So the photocorrosion depends on the photocatalysis run and on the equipment. And so, as I said, it's clear that we need a hybrid system where the weakness of the material can be compensated by the second phase, or we can take advantage by to keep the electronic structure of the copper oxide in the bulk and improve the kinetics of the surface, or to create or to add a catalyst, co-catalyst with the good absorption energy towards copper 1 oxide. And for that reason, we screen the number of dopants we produce over 360 electrodes with 11 cations with 4 concentration, and based on the primary screening, we could choose the best dopants to affect the surface properties, since the Fermi level requires the withdrawal of the electron from the surface. So based on the results of these measurements, we could see that the zinc, nickel, and other cations are worth further investigations. And once we measure the Fermi level, energy, then we perform the other photoelectrochemical measurements like quantum efficiency or solar-2 C products efficiency with parallel detection of the CO2 reduction products. And finally, having all results, we could see which dopants might be the best one if we regarding not only the structure but also the photoelectrochemical performance, and also the photopotential properties, stability and selectivity. And if you see, you can notice on these graphs that in contrast to Fermi level measurements, the zinc in the bulk, it's not the best dopant. So that was the reason that we that we engineer an electrode where the deposition of the zinc hydroxychloride is on the surface, but at the same time affect the properties of the bulk. So based on the electrode deposition process, we produce the copper 1 oxide electrodes, and then by default deposition, the zinc hydroxychloride has been deposited on the top. In that way, we engineered a contact between the copper 1 oxide and the zinc hydroxychloride. And you can see on the SEM picture, this is a very good contact, which allows us to not only protect the electrode against the photocorrosion, but also to create a physical barrier against oxygen, but at the same time allowed charge and proton exchange, so can work effectively in the photoelectrochemical environment. In addition, the zinc hydroxychloride forms a direct contact between the copper 2 oxide. So in the electrolyte, it suppresses the photocorrosion while maintain the charge mobility. And this confirms that the role of copper zinc hydroxychloride can be this kind of composition is very effective as an engineered photocathode architecture designed to combine the absorption enhancement and the surface protection and controlled charge transfer at the surface in the bulk, transfer in the bulk, and the absorption energy at the surface. Here you can see the photoelectrochemical performance of the zinc, of the copper zinc hydroxychloride with the optimization of the running potential, and at the potential 0.4 volts versus reversible hydrogen electrode, you can see the best stability and the best efficiency towards C2 product. Even after 20 hours, you can see the production of ethanol and methane. But what is even more surprising, after 20 hours of stable photoelectrocatalytic activity, in the solution we could detect the higher hydrocarbons as well. So the high selectivity is attributed to the synergetic effect between the zinc hydroxychloride and the copper 1 oxide through the absorption, the higher energy of the absorption of the CO radical and the CO radical intermediates. So in summary, I would like to say that the coating of zinc hydroxychloride can be deposited in a very simple way by the photo deposition. However, it's very effective by creating the intimate contact with the copper 1 oxide, can protect, block the oxygen, and maintain the ion exchange and electron flow in the bulk, and therefore this is a very good co-catalyst, I would say, and can be used for production of higher hydrocarbons. For CO2 reduction, we explore also the metal organic frameworks prepared by the decomposition of the polymer to create a highly developed surface. You can see the principles of the method described already in the literature. And for our application, we choose the metal organic framework based on the copper with the nickel oxide. And through the composition of the nickel oxide, we form different morphology, and we notice immediately that the impregnation and the absorption of the CO intermediates and CO2 radical intermediates are very high at the surface, at the structure, and what is even more, the nickel, we could, by electrochemical approach, we could detect that in comparison of the nickel introduces the mid-gap states, which affect the conduction within the layer and the position of the valence band edges. Here, through the electrochemical measurements, we could check the charge transfer, which has been improved. Therefore, it might be very effective. It might be very effective for the production of CO2 reduction products. Finally, of course, we check the photoelectrochemical performance in the solution, and you could see on the left side the production of how the system behaves in the electrolyte containing the substrate. Immediately we could notice the high photocurrent in CO2 saturated saturated electrolytes, which confirm the active electron consumption by the CO2. And this is kind of confirmation that we have this catalytic activity towards CO2 reduction. So the last information taken from this system, it's very important that the MOF structure has been retained. So it improves the light absorption and charge mobility. So we take the advantage of the MOF itself, and then we add the electronic improvement coming from the nickel in the MOF case, in the MOF cage. So to briefly sum up the copper nickel oxide metal organic framework, it can be used for CO2 reduction with very slight change in the structure by insertion of specific cations. We can affect the catalytic activity towards production of CO2, or we can direct the activity towards reduction, for example, of water, which is much more easy with these materials. However, as we used to work with these materials for hydrogen production, we notice that there are very small changes, very small significant points which can, and we prove that it can be used for CO2 reduction for methanol and ethanol production. This is for sure, and currently we are working on the surface modification to direct the selectivity towards higher hydrocarbons. So with that short summary, I would like to thank to your attention, and if you have any question, I'm happy to answer. Thank you.
Thank you very much, Professor Solarska. Any question? I think we have time for one question.
There is a question in the chat. If you can comment on the thermal stability of copper nickel based MOF.
Did you hear the question?
Yeah, of course.
Okay,
no,
yeah.
I do not see, but I could hear the thermal. You have to draw. I would like to draw your attention that this is not MOF. This is MOF derivatives. So the thermal stability is higher than for MOFs. And with our approach, the MOF derivative, the copper nickel can be stable up to 500 degrees C.
All right. Thank you very much. I think we need to. Any other question? One more question. All right. Thank you very much, Professor Solarska.
Thank you.
We have to move to the next presentation. Thanks a lot. So the next presentation will be given by Mark Fach from Technical University of Darmstadt. And this presentation is linked to Carbio project. I'm the technical coordinator of that project, so listen carefully. And he will talk about fluidized bed oxygen steam gasification of torrefied biogenic residue with an oxygen carrier bed materials. Please, floor is yours, Mark.
Where should I stand? There's a camera, right? So
this is the camera, so you can. No, it's a wide screen. Even from the
like
other
this.
side.
All right. Thank you. Thank you for having me. So as Ali told you all this morning already, the Carbio project did research on and assesses the whole process chain from biogenic waste to biofuel. And what we did, we investigated the gasification as part of this whole process. And there we applied the very common or very proven technology of circulating fluidized bed gasification and used an oxygen carrier as a bed material for the first time. So this again is the whole process chain, and it looks a lot on first glance, but I will walk you through. So at here, there's the food waste or organic waste, organic fracture of municipal solid waste, which first enters a pre-treatment step, drying and purification, where the energy input is or the energy specific is improved. And then this torrefied feedstock enters the gasification and syngas cleaning step. And the clean syngas then can be transformed via Fischer-Tropsch synthesis to either sustainable aviation fuel, or if you focus on the alcohol fraction, for a marine fuel market. And because Carvio is also investigating setting the CO2 fixation and mineralization, this whole process could in the end be associated with negative emissions. And now I will give you in the following slides, I will give you a very brief overview of our findings for the results. I could go much more into detail, but due to time constraints, I will keep it very superficial. But we have at Darmstadt, we have a lab scale reactor, which is a bubbling fluidized bed reactor with 1 kilowatt thermal input. And this one we use to screen the potential bed material that might be, or where there could be improvements, and also screen the different feedstocks that were investigated inside Carvio. And then we also did some pilot scale and syngas cleaning tests with our circulating fluidized bed reactor at 1 megawatt thermal input to, first of all, to demonstrate this novel process, and also to study this process at a more relevant scale and to study the trends and correlations at the relevant scale. So in order to evaluate our process, I will define some process variables and also then some process performance parameters. So on the process variable side, we have the thermal load, which is just the mass flow of the feedstock multiplied by the lower heating value of the feedstock. And we have the equivalence ratio, which is the mass flow of the actual oxygen input divided by the mass flow of the oxygen that would be needed for full combustion, and the steam to biomass ratio, which is the mass ratio of steam to feedstock. The process performance side, we have the cold gas efficiency, which quantifies the energy that's converted from the feedstock to the H2CO and CH4 species. And also the carbon conversion efficiency, which quantifies the amount of carbon that gets converted from the feedstock to the syngas. You can calculate it in two ways. You can also assume 100% and then subtract the 100% with the carbon that enters the system in solid state in the fly or the bottom mesh. This is our lab scale reactor or lab scale test setup, where we have a tube that is externally heated, and then there are gases or gasification agents fed from below. We have here a screw feeder that feeds the feedstock continuously inside the fluidized bed. And then in the flue gas pad up here, this is needed so that we can quantify our syngas composition. For the feedstock screening, we used 4 types of feedstocks. The first feedstock is torrefied kitchen waste, representing the organic fraction of municipal solid waste. Second one is torrefied corn residue, which was the only commercial feedstock that we bought from the vendor. And then 2 other project-related feedstocks are torrefied waste cellulose pulp residue and torrefied cherry pits. Now on the right-hand side, for those 4 feedstocks, there are test results, all of the bed material ilmenite and at reactor conditions of 850 degrees Celsius. And what you can see there, based on those efficiencies, both the carbon conversion and the cold gas efficiency is highly dependent on the feedstock, actually, with torrefied cherry pits performing the worst and torrefied kitchen waste performing the best. For our bed material screening, we first applied quartz sand, which is an inert bed material and is very commonly used in fluidized bed technologies. Then we also used olivine, which is often used because it has some catalytic tar cracking abilities. And the lower ones are the oxygen carriers. There we have ilmenite and also LD slag, which is a residue from the steel industry. Again, the results for all those bed materials, they were done with the feedstock torrefied corn residue, and again, same process conditions at 850 degrees Celsius. And you can see that all of those active bed materials, all of those are performing better than the sand. And olivine performs the best for the cold gas efficiency, and LD Select shows the highest carbon conversion. So for our pilot tests, we have our circulating fluidized bed reactor inside our high temperature process facility, where we also investigate other fluidized bed related technologies, for example, chemical looping. And then next to this facility, we have our syngas cleaning plant. And next to the syngas cleaning plant, we have the synthesis test rig, which was not part of the Cabio project, but with which we can then demonstrate the full process from gasification to synthesis. Due to the substantial size, this reactor needs to be operated in 3-shift mode with early, late, and night shift. In those tests, we applied the bed material ilmenite because we had sorting problems with the LD slag. And for the feedstock, we first used wood pellets because it's an easy material for the startup of this system. And then also torrefied corn residue. Like I said before, this was the only, or this one was a feedstock that we bought from a commercial vendor because we needed 30 tons of material that we could not produce ourselves inside the project. So then we operate our reactor according to the process conditions until the system reaches a steady state. And then during the steady state, we take offline samples in order to balance or quantify all of those input and output streams. That's something that we call balance points. And something that we call data points is just the mean of 25 minutes of online data. And we use that one to investigate more the correlations and trends of the process itself. So some exemplary balance point for the wood pellets operation with at 830 degrees of Celsius inside the reactor, an ER of 0.25, and steam to biomass ratio of 0.66. You see here all those input and output streams. You see that the syngas is the most substantial output stream, with the fly ash significantly lower, the bottom ash even lower. Compared to an exemplary balance point of the torrefied corn residue, where we had a lower ER and a higher steam to biomass ratio in order to reduce the temperature a bit to 780 degrees. And you can see this is done by just increasing steam input. So here for the torrefied corn residue, we have here 50 kg per hour more steam than for the wood operation. The syngas stream is still the most significant output stream. However, now the fly ash stream is also much more at 60 kg per hour. And this was not only a large amount of stream, but this was made out of very, very fine particles that led to problems in our flue gas tract. And because this fly ash stream had such a large carbon composition, it also significantly reduced our process performance of the torrefied corn residue, which we will see now. Here is first the carbon conversion for the same balance point as before. For the wood pellets, it sits at calculated both ways at 92%. But for the torrefied corn residue, it's much lower at 70 or 61% respectively. And for the cold gas efficiency, which is here plotted over the reactor temperatures, you can observe similar trends. The cold gas efficiency from the torrefied corn residue operation is much lower than for the wood pellets operation, and also not satisfactory. For the wood pellets operation, it is acceptable at 65 to 70%. And what you can also see there that the cold gas efficiency for the wood pellets does not really, or it's not correlating to the reactor temperature. So there must be other underlying correlations there at hand, which still needs to be investigated. The syngas quality, however, was more favorable for the torrefied corn residue, where here is the methane load, or the feedstock specific methane load over the reactor temperatures plotted there on the left-hand side. And you can see that it's for the torrefied corn residue, it's much lower than for the wood pellets. So less energy ends up in the methane, which is better. What else you can see there is that there is a positive correlation for the wood pellets over the reactor temperature, which is likely due to the cracking of heavy hydrocarbons at higher temperature. The H2 to CO ratio is also more favorable for the torrefied corn residue at a higher value. However, this one is heavily influenced by the equilibrium of the water-gas shift reaction. And you can also see it at the trend here. You have at a higher temperature, you are producing more CO due to the equilibrium. So coming to the conclusions, we definitely saw that the catalytic active and oxygen carrier bed materials enhance the process performance and the syngas quality. Also, we observed that the type of feedstock has a very big impact on the gasification performance. The successful demonstration of the novel process at pilot scale, at 1 megawatt scale, was achieved for our wood pellets, but for the torrefied corn residue, there needs to be a refinement of the ash handling, which sounds very bad, but for me, it seems there is a very straightforward solution. You could either optimize the cyclone for the present process, or you could operate 2 cyclones in series, where the other one is more optimized for the lower particle load, which is also quite typically for fluidized bed operations. And now this data, which is very close to industrial scale, is the basis for effective scale-up, and this is now being assessed inside or incorporated in the Carbio process chain for our life cycle assessment. So thank you very much for your attention.
Thank you very much, Mark. Questions, please. Thank you very much, Mark. Thanks a lot. The next presenter already here, Professor Konsolakis from Technical University of Crete, and his presentation is linked to the project Ecolefins, if I tell that right. And he will be talking about rational design of non-noble metal nanostructured catalyst for CO2 hydrogenation to value-added products. Please.
Thank you very much for the introduction. Good afternoon to everyone. Before proceeding to my talk, I would like to take also this opportunity to thank all the members, all the partners for this initiative and the organization of this workshop. As already mentioned, I am Michalis Konsolakis. My background is chemical engineering, and I am professor at the Technical University of Crete, one of the main academic institutes participating in the Ecolefins project. In the next 15 minutes, I hope so, I will try to show you how catalysis could become the vehicle for circular economy and sustainability through the rational design of non-noble metal nanostructured catalysts for CO2 activation to value-added chemicals and fuels. Now, regarding the Ecolefins project, our target is to electrochemically convert carbon dioxide and steam to light olefins in coionic membrane reactors. One of the main objectives of Ecolefins project is to develop cost-efficient and highly active electrocatalytic materials for CO2 activation. Thus, in my talk, I will focus on the fine-tuning engineering strategies that could be applied in order to adjust the local surface structure of earth-abundant metal oxides, and in specific on the size and shape engineering at nanoscale. And then we will see the implications of these fine-tuning strategies on carbon-catalyzed reactions, in specific on CO2 hydrogenation to methane or olefins over nickel or iron-based catalysts. A lot has been already mentioned about the carbon dioxide and the different mitigation technologies. Thus, I am not going to stay further on it. Just to underline that carbon dioxide originated from fossil fuels accounts for about 65% to greenhouse gases. More worryingly, and according to the future projections on global energy demands, this situation is not going to be changed in the near future, especially in emerging energy markets. Thus, there is an urgent need to turn to more sustainable and environmentally friendly solutions. We said the carbon capture and utilization technologies, instead of single carbon capture technologies, gain particular attention since they can provide the required circular economy and sustainability approach. And among the CCU technologies, the catalytic upgrade of carbon dioxide to various chemicals and fuels offers the opportunity to combine the captured carbon dioxide with green hydrogen derived from renewable energy sources, thus further contributing to the sustainability of the overall process. However, we are all aware that this process, the CO2 hydrogenation, suffers from significant thermodynamic and kinetic restrictions. In other words, it is impossible to be carried out without the use of highly active catalysts. Thus, and at olefins, our efforts have been focused on the rational design instead of following a trial and error approach to synthesize cost-efficient and highly active catalytic materials. Let's at first exemplify this rational approach on the basis of the CO2 hydrogenation to methane through the Sabatier reaction. For this particular reaction, the most active catalysts are noble metals, like ruthenium, which exhibits a favorable deep center position in conjunction to high hydrogen dissociation ability, thus offering excellent methanation performance at very low temperatures, but with a cost of about 10 to 15,000 euros per kilo. On the other hand, transition metals like nickel exhibit, of course, a much lower cost by about 2 to 3 orders of magnitude lower compared to ruthenium, but also shows a lower demand center and a moderate hydrogen dissociation ability, thus requiring much higher temperatures than ruthenium in order to achieve the same conversion levels. Thus, in this case, in the case of CO2 methanation over nickel-based catalyst, a rational design approach should be focused on the optimization of CO2 activation by employing, for example, as I will show you later, highly reducible supporting materials, and by the improvement of nickel dispersion and metal support interactions in order to adjust the deep band center and the hydrogen spillover. On the other hand, for the most demanding process, for the CO2 activation to olefins, the state-of-the-art catalyst involve iron-based multi-component catalyst for the Fischer-Tropsch route, or zeolite-based materials for the methanol-mediated route, both suffering from low activity, broad product distribution, and complex composition. In this case, a rational design approach should be focused on the enhancement of CO2 activation via the formation of active phases, like carbide phases, and to the adjustment of acidity and oxygen vacancies to regulate the selectivity. In this point, a key question raised: is it possible to adjust the intrinsic properties of nickel or iron in order to develop highly active materials? Thanks to the huge progress so far achieved in the nanosynthesis and surface science, the answer is yes. And this can be achieved by advanced synthesis or promotional routes at nanoscale and through the combination of different transition metals in order to take advantage of the synergistic interactions between them and from the interfacial activity. In this point, I'd like to briefly mention some fundamental aspects about the size and shape engineering. It is well known that by decreasing the particle size down to nanoscale, significant changes on activity and selectivity can be obtained, and this can be attributed to different factors involving, among others, the increase of surface to volume ratio, the facilitation of structural defects and oxygen vacancies, and last but not least, to the development of peculiar metal support interactions that which result on interfacial sites of unique reactivity. Besides, however, the significant modifications that can be achieved by decreasing the size down to nanoscale, another adjusting parameter is the shape, the so-called facet-dependent reactivity. In particular, the catalytic activity can be notably affected by the preferential exposure of specific, as you can see here, crystallographic planes on the reaction environment. And this is due to the direct impact of morphology on the energy formation of anionic vacancies as well as on the modifications on local surface structure and chemisorption properties. Overall, we can say that metal nanoparticles of tailored size and shape could play a dominant role in catalysis. Let's now proceed to the implications of these fine-tuning engineering strategies, starting from the Sabatier reaction over nickel-based catalysts. In this case, the rational design methodology that is followed involves at first the serum oxide as supporting material due to its well-known versatile redox and electronic properties. Then we try to fine-tune the serum oxide structural and redox properties by regulating the size and shape. And lastly, regulate the nickel dispersion and metal support interactions by controlling the nickel particle size. By following the hydrothermal method and adjusting various parameters involving the concentration of precipitating agent, the aging time, and temperature, we can regulate nanocrystals nucleation and growth, thus obtaining different nanomorphologies like nanorods, nanocubes, or nanopolyhedra. Here you can see some indicative TEM images revealing the formation of nanorods with a mean diameter of about 15 nanometers and the length varies between 50 to 300 nanometers, nanocubes, and nanoparticles with an irregular, let's say, polyhedra-like shape with a very low size of about 10 nanometers. What happened? Okay. Here you can see at a glance the main textural characteristics of fast-prepared nanoparticles. Nanopolyhedra exhibit the highest surface area, followed by nanorods and nanocubes. And here are the hydrogen TPR reduction profiles of serum oxide nanoparticles of different morphology, nanopolyhedra, nanorods, and nanocubes. Two peaks are observed. The first one is related to the reduction of surface oxygen, whereas the second, at higher temperatures, to the bulk oxygen. Notably, quantitative analysis here revealed that the surface to bulk oxygen ratio follows this order: nanocubes, nanopolyhedra, and nanorods. That is, nanorods exhibit the highest population of loosely bound oxygen species. And this is further verified by in situ Raman spectroscopy, which clearly reveals that the ratio of D to F to G band, which is indicative of the population of structural defects and oxygen vacancies, follows this trend: nanocubes, nanopolyhedra, and nanorods. Overall, nanorods exhibit the highest abundance in defects and oxygen vacancies. And here we can see the output of this fine-tuning strategy: the CO2 conversion and methane selectivity of optimized nickel Syria nanorods catalyst in direct comparison with a nickel supported on amorphous commercial Syria sample. The superiority of nickel Syria nanorods, both in terms of activity and selectivity, is obvious. It exhibits an excellent methanation performance, achieving the equilibrium predicted values at very low temperatures at about 300 degrees Celsius, accompanied at the same time by complete selectivity methane. Very recently, in an effort to further enhance the low temperature methanation performance below the 300 degrees Celsius, we try to adjust the nickel particle size. Thus, we incorporate nickel nanoparticles into Syria nanorods in order to obtain, as you can see here, a range between 10 to 25 nanometers. And here you can see at a glance the catalytic evaluation results in terms of side time yield as a function of nickel particle size, carbon dioxide conversion, and methane yield. The best performance can be obtained by a nickel particle size of about 20 nanometers, offering a yield to methane of 90% at about 250 degrees Celsius, surpassing the state-of-the-art ruthenium-based catalyst, thus demonstrating the effectiveness of the proposed fine-tuning approach. Let's now see the corresponding strategies in the case of CO2 activation to olefins, the most demanding process, instead of methane. In this case, The adjustment parameters involve the iron size and shape, the use of specific pretreatment protocols in order to obtain highly active carbide phases, and the use of bimetallic phases to take advantage of the synergistic interactions between iron and other transition metals, as I will show you later. Again, by following hydro or solvothermal methods and adjusting the solvent, the participating agent, chelating agent, we can obtain different nano structures, nanocubes, nanopolyhedra, let's say, clusters, and nanospheres. At first, we explore the effect of different pretreatment protocols by the iron nanoparticles being imposed calcination in air, reduction in hydrogen, or pretreatment under carbon monoxide. And the results clearly reveal that CO pretreatment results in the best textural properties in terms of BED surface area and pore volume. Notably, XRD analysis reveals the formation of iron carbide phases only under CO pretreatment. Later, the hydrogen activation or calcination will be a result on the highly active carbide phases. And here we can see the CO2 conversion, the yield to olefins over an iron commercial sum, iron nanocubes, nanospheres, nanoclusters, and nanopolyhedra. And we can see that nanopolyhedra exhibit the best performance, offering about 40% of carbon dioxide conversion and a selectivity to olefins 28%, yielding about an olefins yield here about 10% to 11%. Motivated by these results, by simply fine-tuning the iron nanoparticles, then we proceed to the synthesis of bimetallic nanoparticles, cobalt iron nanoparticles of different composition. Extended physicochemical characterization of cobalt iron nanoparticles of different composition reveals that there is an optimum ratio, an iron cobalt ratio of about 5, which results in the optimum textural properties on enhanced formation of active carbide phases, and also in abundance in medium to strong basic size. And here we can see the CO2 hydrogenation performance of bimetallic catalysts of different cobalt iron ratio in direct comparison with the same iron nanoparticles. As you can see, the optimum performance is observed for this ratio, resulting in a yield to olefins of about 16% instead of 11% over single iron nanoparticles and only 1% over iron commercial sum. Thus, we managed to increase the yield to olefins by 1% to 16% over the same material, iron. Thus, in conclusions, we can say that by co-adjusting the size, the shape, the composition and pretreatment conditions, highly active and selective catalysts can be obtained for CO2 hydrogenation. Earth-abundant metal oxides with a comparable or even better reactivity can be developed, providing thus the materials flattened for real-life energy and environmental applications. However, it is of particular importance to capture all these size and shape effects under real working conditions through the use of operant characterization techniques in close collaboration with computational studies in order to disclose reliable structure performance relationships. Before closing, I would like to thank all of our students, PhD, postdoctoral students, my colleagues in the Olefins project, and of course to acknowledge the European Union for the financial support through this program. And I would like to close with my favorite quote from the ancient Greek Aristotle. There is only one way to avoid criticism. Do nothing, say nothing, and be nothing. And since I have already said something, I am ready to accept your criticism and questions. Thank you very much. I hope
Thank
your
you very
time.
much. Yeah, it was very good, Professor Konsolakis. Any question, please? Yes, please.
We have a distribution of the light olefins.
Yes, very good question.
Any trend in selectivity?
Here.
Everything.
The different colors correspond to the selectivity to different products, methane, carbon monoxide, and this color corresponds to light olefins, C2 to C4. And here, the selectivity is about 28%.
Because we have to move to the next presentation. The next presentation goes to Dr. Mara de Joannon. I hope that I'm pronouncing it correctly.
Perfect.
Yeah, from CNR STEMS in Italy. Then it's linked to the project Minicore, and she will present mild combustion and dry reforming for CO2 and pyrolysis byproducts valorization. Thank you very much, and the floor is yours.
Hello, everyone. Yes, I am partner of Minicore project. It is a project founded by European Aviation Council, and it started in 2023, but we have still a long way to go. This is the partner of consortium. So I am not the coordinator. The coordinator is Lund University, and in particular Christian Brackman. And we have also other two members of the consortium, DTU and RIXA. And I mean, the Minicore project is focused on building up an integrated process to use waste and residual biomasses to build a value chain producing energy, syngas, and biochar. Why these? Oh, sorry, maybe changing the computer. The CO2 is. Okay, it's not reported well, but utilizing CO2 and producing biochar for nitrogen uptake. Why? Because okay, this is our interest, but we were in a IAC project challenge call, and where there is also a portfolio. Do you know how to? I don't know if you are aware about AEC framework. They put together a project with a similar challenge. In this case, the challenge was CO2 and nitrogen valorization and management, focused on very different topic too, to push on such a specific topic. So I don't want to talk about the wood project because tomorrow my colleague will do it, but I just want to focus on two of the key enabling technologies of all these process that start with pyrolysis for treatment of biomasses, but there are other two key steps that are mild combustion and reforming that are enabling technologies for the use of bio-oil and biogases produced from pyrolysis. So let's start from mild combustion. I know that I am on the other side of the street because I'm talking about homogeneous homogeneous conversion process. But here I see that the people is much more devoted to heterogeneous processes. What about? So I spent a few words on mild combustion. What is mild combustion? Is what they say. I define the other side of combustion, because here you see a standard flame. Here you see the system where a combustion process is going on, but you don't see any flame structure. Okay, before they were the video, and this was the process going on. So what is the difference between the two processes? That locally this mild combustion occur where there is a very high temperature locally, so higher than ignition temperature of the mixture, but very diluted reactants in such a way that so diluted that the increase of temperature is very low. This is just a formal way to identify the mild combustion. So you have very low temperature increase that does not allow to sustain the standard flame, and so you cannot have the standard deflagration process of the flame, but the process is based on auto-ignition of the mixture inside the reactor. And of course, these two points, high temperature, local high temperature and very diluted reactant, can be obtained with internal recirculation. So we cannot look at a process where you have to feed diluted, you're not forced to feed diluted reactant or something to dilute the system, but you can have, due to very particular, very specific fluidodynamic field, reach locally such condition. This is one of the case. So with respect to, just to give go a bit more inside, if you go on the map where we have the local temperature of the reactor and the oxygen in the local condition, you see you can place the different kind of conversion that we identify as combustion. The typical one with the flame front propagation is placed in this way, in this place, mild combustion in this way. So it is characterized by very low temperature increase, but very high initial temperature. And I always refer to local condition. Okay, so what are the points of using mild combustion? Putting together all these characteristics, so low maximum temperature dilution, preheating is not, I told you, not external preheating, but local. So it's more or less like the circulation. You have very characteristic process. It is flameless, as you see. It's noiseless. So you, in a big system, you can avoid all problems related to, for example, in gas turbine with humming and so on. It is also it's also characterized as a very uniform, because no flame front, very uniform temperature and concentration profile. But why in a mini core? Because it is intrinsically stable. It's that this give to the process high fuel flexibility. Okay, so indeed we already tested this process with many fuels, ammonia, or alcohols, and other paraffin, but also hydrogen, because also hydrogen is good to be used with mild combustion, because with local, the main problem of hydrogen utilization in combustion process is very high, laminar flame speed that you cannot control sometimes. So often this is the main problem. So the point is that you dilute, you can locally dilute, and so you can easily use also hydrogen. But this is the other side of the problem. So what happened on bio-oil and biogases that we have as the product of pyrolysis? We already did experiments in our very characteristic burner that has a cyclonic fluidodynamic configuration that is that allow us to stabilize very easily the mild combustion, and it also works at from 1 to 50 bar. That is also a future key point. This is the aim to utilize the biogas and bio-oil in this burner. That will be the final point. But we generally use, a scale bridging approach, starting studying the processes, looking at the kinetics in a zero-dimensional reactor, as jet steamer flow reactor or tubular flow reactor or counter diffusion flame and so on. So for building up all the steps from kinetic model optimization, kinetic that allow an easier design of an optimization of the process. We in the past this is just a view to see how how change the calorific value from, for example, pure methane or the pyrolysis gas. So this is just to give you an idea on the issue that you have, because in stabilize, in converting in standard process the biogases. And in the past, we tried to do to stabilize the biogas conversion in mild condition, looking at the biogas obtained in different pyrolysis process for utilizing cornstarch, rice husk, and pine. Okay, and we find that this is not part of Minicore. This is the step before Minicore. We had very good results directly in the burner that I show you, the cyclonic burner. But we miss the step before that. We need to expand our study. So we started to study in the zero-dimensional burn reactor, that is a jet steamer reactor in stems, with the different composition that we had with new starting from new biomasses. But our aim is to be independent on the biomasses and to test a surrogate mixture with different composition of CO, hydrogen, methane, and so on, in order to have a very wide view of the and a really useful data set for model optimization and design. So which kind of information we have from 0D jet steamer flow reactor? For example, of course, the species concentration, the range of stability of the process. In this case, is reported just to give you an idea on the as function of CO2 ratio. And also identifying very peculiar condition behavior as instabilities that are very important, because allow us to better optimize the kinetic model. Why? Just in addition to that, biogas is, let's say, very simple composition, because you have methane, CO, hydrogen, and so on. So we can imagine that the kinetic model are all already there to be used and to be tested for design. This is not really true, because the presence of species like CO2, for example, that have never very few, there are very few studies on that. The presence of species like CO2 or however working at very high dilution that are needed for using biogas from pyrolysis totally change the kinetic or the balance between among multi paths that are present in the kinetics, oxidation kinetics of this kind of species, CO, methane, and I have to say also hydrogen. It's incredible, but it's true. So we will doing so all this stuff for enlarging the study on biogas composition, and of course the same approach will be done also for bio-oil conversion or oxidation. Of course, you know that bio-oil that we obtain is a very complex mixture where we have alcohol, aldehydes, ketones, acid, sugar, and of course with different composition. And it is very similar that there are very few, but I would also say almost no data on the conversion of single component of the bio-oil. And so it's in the model available, the kinetic model available are very empiric. Okay. So the aim of the study is to do a characterization of bio-oil oxidation, looking at the single component, and in order to put together a strong data set that can be used for model optimization and the future design of the mini-core process. So this is for oxidation. The problem is even more, let's say, challenging for the reforming step, because we are not looking at catalytic reforming. Generally, in literature, you can find plenty of papers about catalytic dry reforming. But we are looking at non-catalytic dry reforming to avoid the utilization of critical materials, the critical metals, and because it is much more flexible with respect to the feed composition, so avoiding poisoning of catalyst and so on. Of course, why we are not information about data about non-catalytic dry reforming, very few in literature, because we need very high temperature. The point in mini-core is to be able to use the mild combustion that allow you to utilize very low calorific value that fuel that generally cannot be used or can be used after purification or further treatment in order to increase the calorific value. In this case, coupling with mild combustion, we can put together the two processes and take advantage of that, and to use the non-catalytic dry reforming. So also in this case, we have to analyze the single molecules in their conversion. And here in this map, we reported, the typical temperature, not experimental temperature, but numerical one, with the empirical model available in literature to obtain with all these components, main component of the bio-oil, the glucosan, furfural, phenol, viacol, and so on, to have 10% of conversion of CO2. So we see that they are very high temperature. So I said we have planned to have the full path from kinetic study from zero-dimensional, starting from the analysis on zero-dimensional reactor, then to go up to the cyclonic unit. And so we started with the single component. For example, this is just an example with the furfural that we had in tubular flow reactor. One of the tubular flow reactor we have, and we can look in this case, the temperature where there is the activation of the CO2 with the CO2 decreasing and CO2 increasing, H2 increasing, and also the composition of intermediate product as in this case methane, because of course there is a step of decomposition of the reactant. So this is just to give you a flavor of what is going on. And what are the challenges for direforming studies? I told you there are very few data. This is because it's not simple to carry out this kind of tests. And so we need to have a systematic approach looking at kinetics of the single component and to have to develop optimized model, but also if because of very complex system mixture that we have to manage, also to have a database for data analytics that could be used for optimization of the final process. And what are the challenge? I talk about mild combustion, dry reforming that have to put in some way together, integrated. And so one of the challenge of mini-core process is to integrate these two processes, and of course the scale up of the system, because this AEC Pathfinder is a TRR3, the final. So we have still 3 years to reach our goal, but the TRR3. But we have to look at these future points. So I want to thank you, the European Commission, to support us, and my colleague, and of course all this stuff will be also performed in collaboration with, for example, London University, because we will do experiments applying chemical analysis. But it is very important. I show you how different is the combustion process in mild condition, so that the identification of intermediate locally can strongly help the modeling of the process. And so we will have Luna will perform optical diagnostics on our system, as well as DTU will support and will develop the kinetic model and will optimize the model based on this on the data we will be able to collect. So that's all. Thank you very much for your attention.
Thank you. Thank you very much. Very interesting. Any question? Please, one. We have time only for one question. So you got it.
For the 0D tests for the mild combustion, was it always 50% nitrogen dilution?
No. We can change in that system. We can change as we want the composition. Okay.
Because I was expecting like this would probably also hesitant.
Yes. So we will test different, and when you use nitrogen, it of course will impact, but it is even more impacting the change of, for example, CO2 concentration. Yeah. Even if you have, you are feeding CO2, but if you feed in excess, they change because there is also. In the past, looking at mild combustion, you have a generally local diluted condition for recirculation. We found a lot of influence on kinetics of, for example, methane locally, and so it's the kinetic model that were used since 20 years was not able to reproduce the behavior in a mild combustion. So yes, we can change, but I have to say that not only in jet cylinder reactor and in plug tubular reactor, we can change as we want. Okay. In burner too, but of course you have the coupling of fluid dynamic fields and but in the power. Okay, thermal power, yeah. But you can change as you want the feed.
Yeah. Thank you. And one more question. I cannot say no to you.
Sorry, I left for a couple of minutes. I don't know if the question was already asked. Sorry for that. Since you have very localized high temperature, you also mentioned that you have no pollution. How is this?
Yes, yes, this is a way of describing the stuff that I missed it because yes, I have local high temperature. I mean higher than the ignition temperature, but because of dilution, you have very low increase with the respect. Yes. This is why you cannot stabilize a standard flame. You cannot propagate the flame because you have not the right feedback, thermal feedback from the flame front. Okay, so you have locally you have if you look at microscopic level, you have the reactor, the burner filled of a small kernel that evolved by themselves independently based on auto-ignition.
Thank you very much, Professor Joannon. Thank you. So the next presentation will be given by Dr. Fredrik Osler from Lund University. And this is also linked to Minicore project. So it was nice to join these two presentations, one after another. So Dr. Osler will talk about biochar synthesis and characterization for soil amendment applications and environmental control. This floor is yours.
Okay, thank you. So my background is much from carbon science and combustion, and recently also connected to hydrogen and biochar. So it's one part of it. And biochar is important because it has several aspects that of interest because it can work as a carbon sink and it can also be a valuable material for further use, and it can be stored and used later and used for different applications. So a short background. The biochar synthesis in our case concerns pyrolysis and slow pyrolysis. That's about a rate of temperature increase 10 degrees per hour. And model biomass we use is hardwood, softwood, and straw. And the characterization is based on, and the chemistry is based on XPS neutron bulk and surface diagnostics and chemistry analysis by elemental approximate analysis. And we do also porosity, pH, and ammonia test, but I won't take up these ones because there's not enough time, and that's our collaborators in which we collaborate in Italy, and they do a wonderful job there. They report some FTIR data that. So what is interesting now, this presentation is focused on nitrogen doping. And we have two types of doping. One is pre-doping, that is you dope the biomass before you pyrolyze. And the other one is that you use pyrolyzed biochar and then you dope it and characterize it. And this is interesting because in the first case, it comes into play with the pyrolysis chemistry. So that will alter it will come in and play a role in the chemistry and give a final product of the biochar, which is different than you would expect in the second case where you do doping afterwards. And that can be interesting for different applications, and in particular for soil and environment applications in our project. And finally, a small outlook. So the background of our two groups in Italy. So you can say that the group in Italy is more specialized towards chemical, fluid mechanical, and environmental with respect to combustion and in particular for the, oh, sorry, which is, doesn't, okay, for the biochar soil amendment case. As you can see from I took one paper which I think is very interesting to characterize their role and in this case. And the other one is the biochar using a new technique for the study dynamics of hydrogen loss pyrolysis. Okay, so biomass pyrolysis is a basis for producing biochar, and you can produce biofuel from a pyrolysis as well, but focus on this. And we see how it interacts with nitrogen, so you can both give, nitrogen gives input to the biochar, and biochar can also interact with nitrogen in the surrounding, like nitrates, and filter them up or release nitrogen through fertilization. And it can also be a source for interesting materials like supercapacitor, electromaterials, filters, and it is. Okay, so and so here we see a typical gravimetry curve, and this is a mass ratio when you pyrolyze. And from neutron attenuation, you see that it gets different here, and that is due to the hydrogen which is lost because neutrons are very sensitive to hydrogen, which you will see later. So the softwood choice in our case it's Scots pine, and the hardwood is European beech, and then wheat straw. These are woods that are of interest in our group. And what is important between softwood and hardwood is that they have completely different characteristics in the capillary structure and how they behave under chemical exposure, dopants in our case. And wheat straw is interesting for instance, in Nordic countries, in Denmark, where there is a lot of wheat, and they can use that as a fuel in their production. And that can also produce some kind of pyrolyzed char material. Okay, so we work under atmospheric pressure conditions using nitrogen or argon. And we use a temperature ramp and a holding time to wait out the pyrolysis. And for lower temperatures, in particular around 360, you have to increase the holding time because the chemistry is much slower. And the dopants we chose are nitrogen dopes. And the principal one is urea because it's strongly connected to manure and natural sources of nitrogen. And it's a pure chemical compound. Other ones that we don't describe here is sodium-based carbonates. Okay, and this I've described. Post-doping is produced by subjecting the char material in a rich water solution of dopants, and then it's dried. And in pre-doping, we use the same procedure, but before the pyrolysis, and then we dry it. Okay, so you see as you go up in temperature, biofuel here, and then in the late, where it's already carbonized, you produce these important gases, methane and hydrogen, and this is a range of temperature where you obtain the biochar. The characteristics of biochar here and here are very different from the chemical aspects in particular. So this is a gravimetry example of of pine wood pre-doped with urea. And from that, you can see that our doping that we use gives us that it contains about 10% urea. So that's the level of doping we have. And also from the DSC, the differential scanning calorimetry, you see that the urea here breaks down and gives a signature of imagery. Okay, so if we look at the properties of this biochar, we see that for raw pine wood we have very little nitrogen, and if we take this is raw without soaking its water and drying. This is soaked in water and dried without any nitrogen. It's very low, and then we dope with urea. And we see that we get interesting levels of nitrogen inside, and that's around between 5 and 6% at both the low temperature and what we have as the high temperature in our investigations. And XPS gives also very interesting results. And you can see for the water doped and dried, you don't see any nitrogen at all. And when you go up with the post-doping, so it's 360 and see 360, it's this one here. And then you have the 360 pre-doping, which is, can't find it now. It's this orange. You see that they are different. And the interpretation of this is preliminary, so what I say may be not strictly correct, but this probably is connected to oxygen groups. When you go up in temperature, you will see also differences. So in the post-doping, as you expect, you wouldn't see much difference in the nitrogen peak here. It seems to be a little shifted, although, and for the post-op, we see that it's quite different, and you see this pyrrolic and pyridinic signature, which shows that you have a complete incorporation of carbon structure. So here it has taken a direct involvement in the chemistry of the pyrolysis. Okay, so we combine our experiments between imaging and spectroscopy with neutrons. And what you see with neutrons is that they're hardly affected by the metals here, this aluminum. You see it's transparent, whereas the hydrogen and biomass is a very high absorption contrast. And that you can use, so when you heat up and pyrolyze, you lose hydrogen and it gets more and more transparent. And that can be used. So here's a case for raw woods, and you see that there are slight differences with respect to what kind of dopant you use. And with ammonia, you see that it shrinks slightly. This is a piece of beechwood, 8 millimeter, and these are pine wood of 10 millimeter diameter. Here is beechwood corresponding. Okay. And these experiments were performed at the Oak National Laboratory, Beamline, CG1D in Mars. Okay, so here, what you can do, you take these radiographies, you do a lot of radiographies at different angles, and then you can calculate the 3D density of the in particular of the hydrogen, which gives the strongest weight. So you can see that every dot here corresponds to the linear attenuation coefficient inside the material. So the brighter it is, the stronger the density of the hydrogen in principle. And you see that this is pine wood, has quite a different structure inside the wood. And you see also that beechwood has a high density. And what is interesting here is also that when you dope, you see that pine wood is highly effective, whereas beechwood is. That shows you a very good example of how important nature can play a role in our material. So that it has a high level of architecture in it, which is hard to reproduce by man as well. Okay. The next step is we paralyze it. So here we see the paralyzed, and we see that they get deformed, so they shrink more along the ring than in the radial direction. And this is with ammonium chloride, and what you see is that you see some crystallization of ammonium chloride inside when it's post-doped. And it seems to penetrate less the more paralyzed it is. And you see quite some rim here. So what gives the signal here is basically the hydrogen and the ammonium. Okay. So you trace the nitrogens through the hydrogen. And what you can do is you do a density analysis along the radius here, and you can see that very interesting feature is that where you plot it, you see for the dark regions, there's very low difference between the doped and non-doped. So all the doping seems to be concentrated in these white bands, which corresponds to the narrow capillary region, which is a late wood region, and this is the early wood region. So it shows an inhomogeneous distribution of the capillarities. And here's some infrared spectra. And we see that there are some characteristic band, the carbonated band here, and the aromatic band here. And this ether band, they behave different if you use different carrier gas, for instance, carbon dioxide. So that's interesting for our case, and nitrogen in another case. So this measurement was performed by the group in Naples. And we see that with temperature, the higher temperature reduces oxygen containing groups and enhance aromatic structures. And the carrier gas type bioshock producing CO2 shows stronger carboxyl functional groups than in N2 at low temperature. So they behave differently, slightly differently, or differently between nitrogen and carbon dioxide. Okay, so we have inelastic neutron scattering, and there it can be compared with Fourier transform infrared spectroscopy, but it has a different behavior than FTIR because it doesn't depend on electromagnetic selection rule or transition laws. It has a quite different, so it basically follows the movement of the protons inside the material and how they move, vibrates. So actually you can see modes of vibration, which you can't see with electromagnetic radiation. So in some cases you can see the movements that is not seen with X-rays or laser systems. Okay. So in this lower one, here we have the high temperature, and here the low temperature. In the lower, in the high temperature, you have less hydrogen, so you get a better contrast between the ammonia with the urea and the carbon. And the pre-doped it follows more the water. Okay, so we're closing now. So our results from local studies is we studied the nitrogen content chemical characterization. So with pre-doped, we see we use inelastic neutrons, XPS, nitrogen, and CHN. And with post-doped inelastic scattering and neutron imaging, we see effects of capillary influence and also we see that the XPS gives you quite different behavior with the temperature, which is interesting, and that pine and beech would have different behavior with respect to pre-doping. And that neutron radiography and tomography give important information effects on shape and alteration of structure already at room temperature. Urea appears to be a good candidate as a near nitrogen dopant in terms of pre-doping. And yeah, as I said, XPS data showed considerable sensitivity for differentiating between pre and post-doping at temperature. And INS data is shows to be useful in post-op samples and important technique to inside the bulk of the entire sample, whereas FTR is more sensitive. So it's very hard with, for instance, with the FTR when it gets highly carbonized to see any features with a spectroscopic feature because it gets too attenuated, but not with a neutron scattering. Okay, so outlook. We need to evaluate more systematically pre and post-op samples and dopants, and identify atoms in environmental biocharm that is most advantageous for controlled release. Investigations of urea dop charts and more so related conditions to study influence for different fluids of pH and different chemical properties, except for metals, organic pollutants, and inorganics. And this the group enables will play an important role for us. Is of great interest. And they will also investigate the content of availability and pH studies through 0.0 charge evaluation. Okay, so acknowledge that there are a lot of people. So the spallation neutron source of the high flux isotope reactor at the Oak Ridge National Laboratory at Vision and Mars, and where we did the experiment in March together with Javier and Monica over there, and she is the expert on nitrogen, and she's part of the. She's responsible for the VESPA that they're building spectroscopy. Okay, and acknowledgement goes to the team at the Oak Ridge Vision, Senyanke Mudianya and Luke Damon that help us prepare and measure the samples, and James Torres and Yushan Zhang at Mars, as well as to perform the experiments on tomography and radiography. And Charles Finney, that has been a long-term collaborator in these measurements. And in the XPS, particularly Summer Harris and Ina Ivanov at the CNMS for doing the XPS, which require, you can measure 2 samples in one day. And of course, Monica Harton, that has been I've been collaborating with for many years. And of course, CNR stems for sample analysis and We're very glad to continue the measurements for this project. And last but not least, we received funding from this program for research and innovation. Under grant agreement number 1115506. Thank you.
Thank you, everyone. I think that if there is any question, we can just connect to him or Monica that is here, right? So we will, yeah. So we will, thank you very much.
Thank you.
And let's go to the last presentation by Asier Oleaga from Technalia, also part of Carbio project. And he will present oxy-fired fluidized bed carbonated waste, digital CO2 uptake monitoring, and its use as SCM in lower footprint cement-based products. Asier, are you online? Are you hearing us?
Yes. Yes.
Okay, please go ahead. Floor is yours. 15 minutes, please.
Okay. Okay. Okay, I will talk you about what we done in Carbio project, European funded project regarding to CO2 utilization for mineralization of some waste coming from oxy-firing processes. Wait. Sorry, for some reason I cannot move the.
You have to click on the presentation and then.
Okay. All right. Sorry. This the team involved in this research. We are Technalia and work also with Cementos Group in this task. Well, first of all, what about mineralization? Mineralization is basically to fix the CO2 in some alkaline compounds. This occurs in the nature. Very slow reactions in general, but the accelerated carbonization technologies try to do it in a fast way. We can apply this to some alkaline wastes like mining waste, industrial waste like slags or some ashes. There are some interesting processes of irreversible capturing of CO2 and also to transfer the mineralogy of the wastes to improve them, to upgrade them, and to convert them from wastes to potential useful materials. You can improve things like expansibility and encapsulation of heavy metals and have some good properties. So nowadays in the worldwide there's already some incipient industry about this, about reactors of different kinds and technologies, and start to be products in the market with different wastes and natural products, and supposed to be a boost in next decades for direct capturing and indirect footprint reduction due to carbonated materials into construction products, replacing virgin materials, clinker, cements, etc., etc. So, after this introduction, need to remind a Carbio project. Previously, it's been explained somehow. This is the general outline of the Carbio project, and our goal is to try to work with the ashes coming from the oxy-conversion of the carbon process. Yeah, basically they are bottom ash and fly ashes. So this is the concept we try to apply. We work in Technalias and Crucis to fix the CO2 coming from Carview processes to put it in alkaline waste of the project and use them upgraded for new construction products like for example cements and mortars. Yeah. All this driven by some digital tools to add more efficiency to the project and more accuracy on CO2 quantification. So while we did this to examine different materials, different trials with different bed materials and fly ashes, and not every material can be carbonated. Only alkaline nature having materials. We have two kinds of big currents that are bed materials, then bottom ashes, and filter dusts or fly ashes. And bottom ashes has mainly a very inorganic nature, but some contamination of the ashes or of the dust ashes, and the dust or fly ashes are mainly carbon organic materials. Yeah, so we did some deep analysis of. I'm not going to explain all the details, but different materials. They were more siliceous or less, or more calcium or magnesium bearing materials. For doing carbonation, we need alkaline compounds, some CO2, and some water or humidity environment. In this case, among all the materials, only LD slag based bed materials were really carbonatable. The other ones were really siliceous, like olivine, sands, silica, ilmenite, that can be useful for applications, but not for carbonation. The question is that the maximum theoretical uptake can be 38% per weight, but realistic after looking to the mineral phases, we expected to capture about 150 grams of CO2 per kilograms, yeah, of sample. So the reactors, we have several reactors. We have other ones, but for this project, we use this static one at the left, less than 5 kilograms of volume, of liters of volume for 5 kilograms of sample. Supercritical reactor that works with supercritical conditions, of course, a bit more complex, and a rotatory drum with multi CO2 fluxes connections for scaling up. We did after knowing very well the material to be carbonated, the LD slag. We design protocols, changing variables of pressure, temperature, humidity. The goal is to take the maximum, produce the maximum uptake, and also the reactivity of the material, which is characteristic for doing cement. So we work with low and high pressures, moderate temperatures, different grain size, very fine to coarse, and always solid humidity between 15 to 25, and CO2 100 commercial, pure commercial, because we couldn't have availability of the CO2 coming from the carbon in this project, because it's very complex, well, very costly, and not enough volume. So Carview project CO2 is going to be nearly to the pure CO2 as we use, so it's equiparable. Mineralization can work with very poor CO2 fluxes also, like a flue gas of chimney, but obviously the effectivity is bigger with the pure CO2. We try to control with the classic approach of temperature pressure monitoring the reactor. The results are that well, with static reactor went very okay. We produce capture close to the maximum. With the supercritical, we really were close to the maximum expected capture, but it's more complex with difficulties for getting to the rich conditions without any issues. With the reactor must be really good tuned and demands a lot of energy. And the rotatory reactor worked very well, very scalable, with similar results as the static reactor of smaller scale. So we have result a granular material that was catalyzed, and we did many other testing, but the most principal are calcimetry and TGA to understand how much was the capture, yeah, which were the mineral transformation, yeah. We see that the calcite increased a lot as expected. And also we analyze the reactivity, how it changed not only fixation of the CO2, but also how it transferred to a better product, a better material that can have some sort of activity that can maybe replace some partially some clinker. So you have a direct uptake, direct fixation, and indirect CO2 carbon footprint reduction in case you are able to substitute clinker, which is a high carbon footprint material. So that's the question. So the question in the project is that finally the pilot scale oxy firing decided to use ilmenite and some organic material. That the results were that both bottom ash, ilmenite based bottom ash, and the dust were not carbonatable. So they decide to use these materials for availability and for costs and all that. In this case, the valorization of this product is contemplated as aggregates for mortars, but we follow working with the LD slag because they can be used in these oxy conversion processes. If in the future is more available and reduces the cost of processing, conditioning, and demonstrate that in case you work with it, the result you can carbonate these wastes and you can valorize with in lower carbon footprint materials like cement mixtures. Yeah. Another more innovation point in this project was to use spectral tools for monitoring the reaction. Our aim is to add to the classic reactors for carbonation, to add value with some spectral bunch either by machine learning and deep learning approaches to drive better the process, to do it optimal with the exact time of reaction and more efficient. Quantification of the CO2 captured. You can do a measuring of the CO2 that you capture by different ways, but I think we bet for online measuring of some parameters that will give us a good solution for that. So we employ LIBS, Raman, NIR, ultraviolet, and even vision, but it's not here. But we use many devices. We have a team specialized in this also, not only in carbonation but also in this. There was a lot of difficulties to how to measure, how to data sampling, gathering. It's a tough work, but finally we get a good compromise of data gathering and resources. We measure the non-carbonated material and carbonated material to compare the different signals, and where are the differential signals. After that, we did data processing to understand to put together the data and prepare for running the models, the machine learning models. And finally, we ran the models, and after some time, we understood well how to do a quantification of quantification of new carbonates generated. I mean, after carbonation, you get a new amount of carbonates, and that is the same of the CO2 fixation. You can extrapolate. So the lab classic approach by calcimetry and TGA, thermogravimetric analysis, and the prediction of the model were quite accurate with some statistical data that gave us a good accurate value, and we were very happy with this. Now the challenges are to scale this up and to integrate with an industrial reaction process, which is not easy, of course. So and also to work with not only the carbonatation, the new carbonatation quantification, but also to understand which type of properties are changing, which is the reflect on properties as material grading for cements. So that's all. I mean, conclusion, materials in this project, only LD slag was carbonatable. We get close to the maximum, which is about 150 grams CO2 per kilogram. In this condition, of course, depend of the equipment and the carbonation protocol, you can get more or less capturing. You increase the temperature or pressure, but you need to, but you are complexizing also. And the industry normally doesn't accept too much complex processes and costly, of course. And we get a lot of information from the equipment experience, especially with the supercritical reactors that for us work very well, but it's complex to operate and has some limitations. In the next step, the project is in progress, and the next months we are going to put all these carbonated materials compared with non-carbonate in the cement-based products. And regarding to machine learning, well, we will follow working with these sort of approaches in this project and also in other similar projects also. So thank you. Any question?
Thank you very much. Thanks a lot. Any question for us here? I'm technically coordinating the project, so I don't have any question for you either.
Tired.
Yeah, but then let me ask you a final question, Asir, then to clarify one point that in case of, for example, ilmenite or
Yeah.
other oxygen carriers, do you hear me well?
Yeah.
Yeah, in case of materials or bed materials like ilmenite or ashes that are not carbonatable, then what is the alternative?
Yeah, the alternative, I mean, we are exploring this. Ilmenite for me is not familiar as product for valorization, but okay, you can use it as an aggregate because there are some experiences in using it as high dense concretes and high durability concretes. Also, it has a lot of iron and titanium in the composition, and it's not very complex composition. It has not strange salts or something like that. So the next step with ilmenite is to work trying to optimize the maximum potential of this material, which is strong concrete, so mortars. We will go with mortars, a smaller scale, and also explore the thermal properties.